To start this video, I want you to imagine two different distributions. On the left, we're going to imagine guessing how long 4 seconds is. Now, if you were going to actually do this, first of all, you'd have to be very bored. But what you would do is you'd take out a stopwatch, hit start, and hit stop when you think it's been 4 seconds. You would need to do this at least 100 times, and each time mark on a distribution how many seconds actually elapsed. So anyway, that's the first drawing. Is it left skewed, right skewed, symmetric? Draw what you think it would look like. And on the right, we're going to do a distribution of the heights of women in Pawnee. There's really no reason for bringing up Pawnee in this example except that I love Leslie Knope and I aspire to be her. Really, I just want to narrow it down. Let's not think of all women in the entire world, just one city. We can say there's maybe 50,000 women in the city. What do you think the distribution of their heights would look like? Pause the video, do a quick sketch of those distributions now. Now yours might look a little bit different, but here's what I thought. For guessing how long 4 seconds is, probably most of the time you're going to be right around 4 seconds, or consistently above or below, but you're going to be fairly consistent. You'll maybe have a couple of times where you overguess or underguess, but mostly you're going to be guessing around the same time. For heights of Pawnee women, this is also going to look pretty symmetric. Mostly you have women who are around the mean height, and then you have a couple that are tall, a couple that are short, but mostly they're around the mean height. Both of these distributions have a special name. They are both called normal distributions. A normal distribution is symmetric, it has a single peak, and it has this nice bell shape. These actually come up a lot in real life, and heights of women is actually a great example. Heights of anyone usually is normal, because most of the time you have most people in a community around the same height and only a few tall and a few short. Other examples are like shoe size, sometimes weight can be normally distributed. Another example that comes up a lot is test scores. There are a lot of teachers that aim for their test scores to look normal. They want to see most students get like a high B, low A. Maybe there's a couple overachievers, a couple underachievers, but they want most of their students at like an average score. Normal distributions are so important that they get their own notation. And that notation is a capital N, which stands for normal, and then in parentheses, 2 numbers. The first one is mu, and that mu represents a mean of a distribution. And the second letter is sigma, and that represents the standard deviation of the distribution. Now I'm going to keep writing some vocab here in orange that you might also want to jot down. Before we continue, let's talk about what mu and sigma actually represent. In statistics, a parameter is something that measures a quality about a population. Now, a population is the entire group of people or the group of things that you're interested in. It could be all of the women in Pawnee. It could be all of the people in your neighborhood or at your high school. It could be the entire population of your country. Or it could be even smaller. It could be the plants on your deck. Anything that measures something about an entire population is called a parameter. And usually those parameters are given Greek letters, because I guess they're fancier. The ones we're going to start with are mu, which kind of looks like the italic capital M, and that represents a mean, and then sigma represents a standard deviation. Now, if you're looking at a subgroup of the population, that's called a sample. And if you're measuring a sample, you're using a statistic. Now, a sample could be, maybe you survey 100 random women in Pawnee, or maybe you ask every other student at lunch a question, or maybe you knock on every other door in your neighborhood and survey those people. Those are all samples. They're not the entire population. They're a group of the population that you're trying to use to represent everyone. Anything from that sample is called a statistic. Now, usually a statistic gets a lowercase letter. For means, we use X bar, and yes, this is called X bar. It's literally just an X with a bar over it. And then S is standard deviation, so a lowercase s. So it might seem kind of weird to you that I'm spending all this time talking about letters, but it actually is important. Let's say you're reading a problem about the heights of Pawnee women, and somewhere in the problem it says X bar equals 64 inches. Well, that would tell you that that's the mean of a sample. Not all women in Pawnee, just a sample. But if you were reading and it said mu is 65 inches, that would tell you that that's the mean of the entire population of women in Pawnee. This goes back to what I've said in previous videos. The way we talk about data is really important. Which symbol you use communicates if you're talking about the entire population or a sample of the population. The next thing is also very important, which is why I typed it for you. Both of those distributions are examples of density curves. A density curve shows us all the possible outcomes of a scenario, and the area under the curve is 1. Now take a moment and read the next sentence with me, which means the area under the curve of any section shows us the proportion of all observations that fall in that section. So let's think about guessing 4 seconds. The area under this curve altogether is 1 because this curve represents all the theoretical outcomes that might occur. So that 1 is like a probability. There's a 100% chance that you're going to guess something under this curve. Now let's focus on taking a section like that last sentence said. Let's think about the section, let's say 4.5 seconds to 4.7 seconds. The area under the curve of that section shows us the proportion of all observations that fall in that section. So let's say the area of this little section is 0.015. That means in the population of all the times that you guessed, the proportion of times that you guessed between 4.5 and 4.7 seconds is 0.015. Now some students prefer to think of this as a percent. So let's say it that way. In the population of all the times that you guessed, the percent of times that you guessed between 4.5 and 4.7 seconds was 1.5%. This is a tricky concept to understand. For some students it makes sense once you've done examples. For some students you need to just like reread or rewatch that definition, which is why I printed it here for you. So if that was confusing, you can rewind and listen to that again, or you could just listen to the rest of the video and maybe come back at the end and see if it makes more sense after seeing some examples. So let's get to those examples. We're going to keep talking about Pawnee for pretty much no reason. The distribution of heights of all women in Pawnee. Okay, before we even get to the end of the problem, I'm going to circle the word all women in Pawnee. So we are talking about a population aged 18 to 24, oh, it's a very specific population, is approximately normal with a mean of 64.5. Since we're talking about the population, this is mu. And standard deviation, once again, population, this is sigma, of 2.5 inches. Make a sketch of this distribution and label 3 standard deviations above and below the mean. Okay, so what I'd like you to do now is pause the video and draw your picture on the left. Save yourself some space over here. Do your best impression of a normal distribution, label the mean, and then label 3 standard deviations above and below. Okay, so here's what that looks like. The mean height is 64.5. We've got 3 above. I just added 2.5 3 times, and 3 below. Added or subtracted 2.5 3 times. Okay, now density curves can be any shape. They can be symmetric, they can be skewed, they can be uniform, bimodal, they could be any shape. When a density curve happens to be a normal distribution, we actually know a bit more about the areas under the curve. So here's what we know if our distribution is normal. About 68% of the data is within 1 standard deviation of the mean. So for Pawnee, about 68% of women are between 62 inches and 67 inches. 95% of the data is within 2 standard deviations. So once again for Pawnee, 95% of women are between 59.5 inches and 69.5 inches. And 99.7% of the data is within 3 standard deviations. So once again for Pawnee, 99.7% of women are between 57 and 72 inches. Now these are all approximate. Okay, if a woman who is 73 inches moves out of Pawnee, we don't need to find a woman who's the same height to replace her. It's all approximate. This rule is so important it gets its own name. It's called the empirical rule. Yes, I did have to look up how to spell empirical. I'm a math teacher for a reason. When I learned this, it was called the 68, 95, 99.7 rule, which is more informative but not as catchy. Let's practice using it. About what percent of women in Pawnee are taller than 67 inches? All right, so I'm going to get out a highlighter here, and if you also like color coding things, I highly recommend highlighting. Taller than 67 inches. So here's 67. Taller would be anything in this section. So we're going to use what we talked about up above with density curves. What we need to do is find the area of this section, and that's going to give us the proportion or the percent of women who are taller than 67. Okay, so 67 is one standard deviation above. Now there's different ways of doing this, but usually I kind of split the distribution into two parts. From here to here is 50%, right? This distribution is symmetric, so 50% of the data is above the mean. So what I need to do is figure out what's this little area here, and if I can figure that out, I can do 50% minus that area, and it'll give me the highlighted area that I'm interested in. So to figure out that, let me think about the empirical rule. 68% of the data is within one standard deviation, so from 62 to 67. So 68%. Let's see, if I take that 68 and I divide it by 2, that would give me the area of this region that I colored in orange. So that's 34%. So now if I want to find this blue tail, I just have to do 50 minus 34, which is 16%. 16% of women in Pawnee are taller than 67 inches. Now there are of course other ways to do this. I know a lot of students would prefer to do like 100 minus 68, and that gets you 32, and then they do 32 divided by 2 to get just one tail. That's also totally fine. It's whatever works best for your brain. The next question says about what percent of women in Pawnee are shorter than 62 inches. So if I shade that in, here's 62. Shorter would be over here. Oh, that was weird. Tablet didn't like that. Now you will notice that this is the exact same tail, just flipped to the other side of the distribution. So this question is actually super easy to answer because it's a symmetric distribution. It's going to be the exact same percent as A. So that's one nice thing about normal distributions. They are symmetric, so if you find the tail on the right, it's going to be the same as the tail on the left. The next two are a little bit different, but I want you to try them on your own. So pause the video and try those now. Okay, so once again, there's different ways of doing these, but the way I saw part C was basically in two sections, which I color-coded because that helps me a lot. So in my little sketch here, I thought of the blue section on the left, because 59.5 is 2 standard deviations below the mean, and then the green section on the right, because 67 is 1 standard deviation above the mean. So we have these two sections. For blue, I took 95 and divided by 2, because 95% of the data is within 2 standard deviations. I only want half of that, so I divided it by 2. And then I did 68 divided by 2 to find the green section. 68% of the data is within 1 standard deviation, but I only want the top half of that, so I divided it by 2, and then I added those together. Obviously different ways of doing it, that's how I saw it. And then for D, I did a similar thing. This time we're 3 standard deviations below and 2 standard deviations above. So for the below part, I did 99.7 divided by 2, since 3 standard deviations, and for the above part, 95 divided by 2, and I added those together. I can't overstate how helpful drawings are. You don't have to color code things, but doing a quick sketch, even if it's not that good, can really help you cut down on silly mistakes. At some point I will be making a video with more of these practice problems. This video goes through things pretty quickly, and the only way to get better at these problems is to practice them. So once I have that video made, I will link it here. That way you can get a little extra practice if you feel like you need it. You probably will, because that's how brains work. We need lots of practice to learn things. Okay, now the next question is, what happens if we ask about a woman who is 57.4 inches tall? That was not in our convenient, neat little empirical rule. Well, it turns out there's actually a more accurate way of finding the area under curves without using the empirical rule. Before we get to that, let's think back to the last video. What happened to the mean and the standard deviation of our data set when we converted every single value into a z-score? We did that with the Pokemon HP values. Take a minute, maybe answer that question on your own. When we changed every single value into a z-score, the mean of the entire data set became 0 and the standard deviation became 1. If we can take any data set and standardize it and get it to the point where the mean is 0 and the standard deviation is 1, really all we need is one set of values for a standard normal distribution, and we could use that to find the areas under the curve. So here's what that table looks like. This is just a little piece of it. We'll look at the full thing later. It's called the standard normal probability table. And the word standard is kind of important. The fact that it's called the standard normal probability table means that it represents a data set that's been standardized. So you can take HP values of Pokemon, heights of women in Pawnee, guessing 4 seconds data set. All of those distributions, if they're normal, you can standardize them and then use this table to find the area under the curve. Now that I think about it, I think the Pokemon one was skewed right, so that one doesn't really work. But any normal distribution, you can standardize all the values and then use this table to find the areas under the curve. I'm going to refer to this as the normal probability table or the z-score table. Most z-score tables have a drawing like this, and this is the College Board version, to show you that the table is giving you area to the left. Some tables just straight up say area to the left, but most have a picture. So let's do the example that is mentioned here. Women who are shorter than 57.5 inches. In order to use this table, I have to standardize my value, so I need to find a z-score. Remember that a z-score is the value you are interested in minus the mean divided by the standard deviation. Okay, I get -2.84. Now I highly recommend you draw a picture. It does not have to be pretty. In fact, it might be very ugly. Not bad. -2.84, that's quite a bit under the mean. And this said we're supposed to find the percent of women who are shorter, so I'm going to shade to the left. Okay, now here's how the table works. Along the left column, you can see z-scores. Ours was -2.84, so we're going to find -2.8 here. Along the top row, you can find the second digit of your z-score, so ours was 0.84, so we want this here. And now I just need to find where they intersect, so that would be here. That means the area to the left of 57.4 inches is 0.0023. Written as a percent, that would be 0.23%. Just look at the way the question is asked to decide if it should be a proportion or a percent. That means that very few women are shorter than 57.4 inches, which makes sense. That person is almost 3 standard deviations below the mean. They are very below average in terms of height. For the next couple examples, you're going to need a full z-score table. I'll put a link in the description of this video with the College Board version, but you can also just Google z-score table or standard normal probability table and you'll find tons of versions. Okay, find the percent of Pawnee women who are taller than 67.8 inches. We're going to start by standardizing. I get a z-score of 1.32. I'm going to draw a picture. 1.32 is a little bit above the mean and it says taller, so we want this area. The picture, once again, is so important. I'm not going to lie to you, I had to re-record this twice because I made typos and both times drew a picture and thought, wait a second. So, highly recommend. Okay, now there's a couple pages, or 2 pages of negative z-scores on the College Board version, and then we get to the positive z-scores. We want 1.3 to 0.9066. So once again, these values on the outside of the table are your z-scores. The values inside the table are giving you area to the left. So that's an important distinction. Area to the left of this z-score is 0.9066, but we wanted area to the right. Since the area under the entire curve is 1, what I have to do is now 1 minus 0.9066. Okay, so that is 0.0934. I guess they said percent, so maybe we should write that as 9.34% now that I look at it. 9.34% of women are taller than 67.8 inches. All right, why don't you pause the video and try B and C on your own before continuing. B is a little bit easier than A because it's shorter than 61, so we can just use the table value. We don't have to do 1 minus because the table gives us area to the left, so that's easy. Now for this one, we have two z-scores. We're finding the area between. So this one happens to be symmetric. Our z-scores are positive 0.6 and negative 0.6. There are different ways of doing this, but I'll show you the way I usually do it. I start with the larger z-score, so 0.6. Here we go, so 0.7257. So from here all the way to the end, the area there is 0.7257. And the next thing I do is look up the negative z-score and find the area to the left of that. So negative 0.6, 2743. So now if I want to find the area of just the shaded region, I have to do the larger proportion minus the smaller proportion. 0.4514, which we would say is 45.14, yikes, percent. Not my best handwriting there. There are definitely other ways of doing that. You could find just this tail, multiply it by 2 and subtract from 100, whatever works for you. Now there is a way of doing this on your calculator, and you're going to have to talk to your teacher about what they expect, but I am going to show you because it is very useful and more accurate than the table. Okay, so on your calculator, what you do is you click second, and then the vars key says DISTR above it. That stands for distribution. So click on that. These are a bunch of different distributions we're going to learn about in this course. Right now we're talking about normal distributions. You want to choose normal CDF. Do not choose PDF, choose CDF. Your calculator might give you a menu. If it doesn't, just sit tight. I will show you what you should do. If you get the menu, it asks for lower and upper. That refers to the lower and upper region. So where does your section that you are interested in start and where does it end? So let's just think of this first example here. Our region started at the z-score of 1.32. So if I'm using the calculator, you have to write out what you're using on the calculator. So I'm using norm CDF. My lower region would be, it starts at 1.32. My upper region, so this shading started at 1.32 and just went off to the right, like all the way to the end of the curve. So I usually just say 1,000, just a large number. And then it asks for the mean and the standard deviation. Well, we're talking about z-scores. When we've standardized all of our values into z-scores, the mean is 0 and the standard deviation is 1. You can see that the calculator automatically has those for me. And then I hit paste. Now if you didn't have the menu, this is what you have to type in. You just have to type 1.32, the comma key is right here next to the parentheses, 1,000, comma, 0, comma, 1. So you have to like memorize the order, but some of us have been using the same calculator since the late 2000s and have memorized things, and you will be fine. But if you have a menu, it's just a slight advantage. So we hit enter. There's our proportion. You can see the table gave us 0.0934. The calculator gives us a little more precision, 0.0934175724. So you get the same thing. Now you might have noticed this was based on z-scores. We could have done the exact same thing, but changed this to the actual height. We could have done 67.8 as the lower limit and 1,000 as the upper limit, and then we could change this to 64.5 and this to 2.5. So just to show you what happens, there I've changed everything from the z-score version to the original data, and we get the exact same answer. This is where you'll want to talk to your teacher. Your teacher will tell you specifically what they want to see on a test. I will tell you that any AP statistics teacher will want to see this calculator jargon. In statistics, quite often you can get an answer by just typing stuff into your calculator, but we as teachers want to see where those numbers came from, so we need to see you write norm CDF, low, up, mean, standard deviation. That way, if you have all of this stuff written correctly, and then you accidentally write down 0.934 instead of 0.0934, I can look at that and say, oh, they knew what they were doing. They just read the number wrong. So if you like, you can try using the calculator for those other two. I'm not going to do that at the moment because, like I said, this video is a very quick overview of everything. I will do more problems like this in that previously mentioned extra practice, and I will, once again, link that. Okay, the next thing we're doing is some backwards problems. So, Ann Perkins, beautiful tropical fish Ann Perkins, is taller than 42% of Pawnee women. How tall is she? I call this a backwards problem because it is backwards of what we were just doing. Before we had someone's height and we were finding the percent of people shorter or taller than them. Now we know the percent of people who are taller than Ann, and we need to figure out her height. I'm going to start with a picture. Quick normal distribution. She is taller than 42% of women. So 42% is a little less than half. So we'll call this 0.42. And here's Ann. Okay, so we need to figure out her height. We're working backwards. We're going to start with the area. So let's pull up the table. And instead of looking for a z-score and finding the area, we're going to find the area and look up the z-score. So we need to find the number that is closest to 0.42 that's like in the guts of the table. So I think it would be this one. Yeah, 0.4207 is the closest we can get to 0.42. The z-score associated with that is negative 0.20. So now we know that Ann's z-score is negative 0.20. Now we can work backwards, like we were doing in the last video, and find her height. I'm going to call it A for Ann. And now we're doing a couple algebra steps. Multiply by 2.5, add 64.5. I believe that's Rashida Jones's actual height. I think she's 5'4", if Wikipedia is correct. I need these problems to be accurate, you know? Okay, why don't you pause the video and try part B on your own. There's something we have to be careful of in part B. It says 8% of women in Pawnee are taller than Donna, so that's this area shaded to the right, which means 92% of people are shorter than Donna. So when we look at the table, we need to find the thing that is closest to 0.92. So I go to the table, that's going to be up here somewhere, 92. It's really close. This one, 0.9207, is just barely closer than 0.9192. So we're going to go with this one. The z-score is 1.41. So I wrote that here. Donna's z-score is 1.41, and then we work backwards. 1.41 equals Donna minus the mean over the standard deviation. Once again, also accurate. That is read as real height. Now once again, we have a calculator way of doing these problems. It starts in the same menu that we were just in. So second, and then distribution. Inverse norm is what we want. Normal CDF, we found an area. Inverse norm is backwards, hence inverse. We start with an area. So click enter, and if you see the menu, you're reminded of what you need to type in. So the area, let's do the Ann Perkins problem. The area to the left was 0.42. Now if I leave this as 0 and 1, I'm going to get a z-score because when I standardize all the values in a data set, the new mean is 0, standard deviation is 1. Negative 0.20189. So it's a little more accurate than the one we got from the table, but you can see it's the same. Ann's z-score was negative 0.2. If you wanted to skip the z-score step, you could technically go inverse norm, and then for mean and standard deviation, you could put in 64.5, standard deviation 2.5, and you'll get right to her height, which we said was 64. Here it's a bit more accurate. Once again, if you don't see the menu pop up, you just have to type in values separated by commas. You just have to memorize that it's area, mean, standard deviation. So one more heads up, I think pretty much every AP teacher is going to be the same on this because it's a College Board requirement. But if you're using the calculator to find your work, you do have to include the word area, mean, standard deviation. It's just a little extra layer of proof that you know what you're doing. Now I'm going to be honest with you, when I was in college and I took statistics, I really struggled. And that's because I never understood what a z-score was and what a normal distribution was. By the end of the course, I was drowning. So it's really up to you to ask if you're confused. Find a teacher, find a friend, find another resource online, and make sure that you understand this so well. It's going to make the rest of statistics so much easier.